You've already done this.
What we call degree 1. It's called linear approximation.
No.
Okay. So if I give you a function, right, and I'd say maybe use a linear approximation to estimate sine of pi over 2 and the linear approximation, not wording this very well.
Subtangent.
We would want to enter something like
I would like. Woo, fantastic. That's not sleep. No each grade. So you calculus DC.
Because you need like two x values, like 0.
I know. Yeah. Okay.
Let's center this linear approximation
0.
at 0.
Right. That's probably a bad choice.
Let's make it pi over 4. Trust me, it'll benefit you. Okay, so, you probably haven't heard this language before, right?
Centered at.
Ooh, does that mean that's sort of
Okay, that's your derivative.
Okay, so we want to calculate f prime at pi over 4 for the slope, right? And f at pi over 4 for our point to write our linear
Equation, right? To write the equation of the tangent line.
Yeah.
Sure.
Okay, so what's y prime?
Cosine at pi over 4, which is
Cosine at pi over 4. Anybody?
45. I hear 2 over 2. There you go.
Okay, let's sine at pi over 4.
I hear 2 over 2.
So what's our equation, our linear approximation?
Y minus root 2 over 2 equals root 2 over 2 x minus pi over 4.
Okay.
Okay.
All right, so this is a Taylor polynomial of degree 1.
How do we work in meters?
Okay. And here's why. I'm going to add this across, okay? And again, if you draw sine x, right, our linear approximation is this tangent line. We can estimate the value of pi over 2 with that tangent line, right? So we could plug pi over 2 in here. Correct? And get an estimated value. Okay, is it very accurate? Okay, Taylor polynomials really increase that accuracy. Okay. So this is a first degree Taylor polynomial because that is our function at some value, right? At power 4. Okay, let me write power 4 there. Okay, plus that value is at prime at pi over 4, right?
This is going to be tedious.
What derivative are we using? What derivative is that? First derivative.
First degree.
Degree 1.
Oh.
Wait, how are we deriving and making more accurate?
Okay.
We
So the first derivative goes with the Taylor polynomial of degree 1. Okay. So what you end up with for a Taylor polynomial of degree 1 is y equals f at some value plus f prime at that value and x minus that value. This is called the center of a Taylor polynomial. You good with that? It's all stuff you know, we just added a couple words to it, right? Okay. Here's what a second degree Taylor polynomial might do. I'll show you in the computer. Because there's a website that does this really well. Okay, so we're going to do sine x. We'll center this one at 0. Okay, so there's our first degree, there's our second, there's our third. See how it's getting more and more accurate? Fourth, fifth. Okay.
So we're just graphing the line at a certain point, or we just derive this out until it becomes the function?
That's what you're doing. You derive it, and derive it, and derive it, and derive it, and write an equation, a polynomial. So what you're doing is you're writing a polynomial that matches this curve. Right, so you can get accuracy beyond linear approximations. Okay, let me show you. The slide shows a little bit better.
So how do we know how many degrees to go to?
You'll be told. Degree 5 or 5
use
terms.
Use a Taylor polynomial to the 5th degree to estimate.
Okay, so there's your first degree, right?
Okay.
Okay, the sine x, the second derivative at 0 is 0. It's like, right? So that's why there's no x squared here.
Thank you.
Okay, so sine at 0 is 0. And you know how sine's derivative comes back to sine x every other time? So that all those even powered derivatives disappear because sine is 0. Okay, but you can see.
Is that 7 bang or is that 71? Like exclamation point or is that 1?
You're in statistics. You tell us.
I can't see it. I'm blind.
It's an exclamation point.
Okay, that was my question. Where?
3 factorial, 5 factorial, 7 factorial, 9 factorial.
Why do I know that word about 0 anyways?
Isn't it every multiple, like, it's every multiple leading up to it?
It's every bit number.
Yeah.
So 3 factorial is 3 times 2 times 1.
That's what it is.
5 factorial is 5 times 4 times 3 times 2.
It's like the summation of, like,
Okay.
Gotcha.
Right, so that's sine. Okay. Here, I want to show you e to the x. Okay, there's e to the x, right? Here's a linear approximation. This is all centered at 0, obviously. Okay. So obviously your values, like if you estimated the value of this function with the tangent line, it would be off quite a bit.
Wait, but why is his f prime of a x?
Because of the equation of the tangent line.
Yeah.
F prime at a is e to the x.
Yeah.
What's e at 0?
1.
1 times x minus 0.
Oh, it's because the f prime. Okay, I see,
Yeah.
I see.
Okay. Okay, here's second. That's a quadratic, right?
Sure.
Again, e to the 0, so your second derivative is e to the x. e to the 0 is 1, and then you have x minus 0 squared over 2 factorial. Okay.
Do we have to write it in terms of like that factorial stuff?
Okay, there's the third degree. You can also call this 1, 2, 3, 4 terms. Okay, so those are the two ways you'll be asked to write these. How many terms or what degree?
So the terms would be 2 degree minus 1.
Not necessarily. I'll show you one where it's not the case. I already did actually. So there's 4th, 5th. See how more accurate it's getting? The more farther you go out. And then obviously our picture's not big enough past that point. Sin x. Remember only the odd exponents rule. So 4 terms of sin x are going to be the 7th degree. Okay.
Wait, is the 0 not counted in the term?
That's not a term, it's
only
the
the
value.
Okay.
Yeah. Okay, so that's what Taylor polynomials are doing. They're expanding the accuracy of a linear approximation. Okay, so let me show you how to actually calculate those. Again, it's just a formula. Okay.
It's only like one.
I don't see how deriving it out would make.
It apparently does. The original, I find it.
I know, but like the whole like derivative relations that we learned doesn't make sense.
So, linear approximation versus completely written out Taylor polynomial. It's an approximate, unless you go on writing for infinity, which is not the desire of any of ours, even the most fun mathematicians. Okay. Here's your linear part, right? You don't need this, but it does help. Because 1 factorial is 1, right? It just helps you see the pattern. Okay. Next term, f double prime, a, x minus a squared, and 2 factorial. Again, notice, second derivative, second exponent, second factorial. All those match. Nothing else changes. So you memorize this statement, and all you do is write the third. Okay, what's the third?
F triple prime.
Okay.
Times x minus a cubed over 3 factorial.
And then you can just keep going. Right.
I can try to do the comparison.
Yeah, they take some work, but I'll show you how to organize it so it's really not that big a deal. It's just doing the math. Okay, what is the general term for a Taylor polynomial? F to the nth derivative at a, x minus a to the n over n factorial, if you generalize that statement.
I don't understand this because so like we always know like first derivative is like slow and like second derivative is compounding. How come when you keep going, it makes it go closer to 1?
Good question. Okay, so I don't have an exact answer for this, but you can reason this through, right? Okay, we looked at a linear approximation, linear.
Yeah.
Correct? Okay. What would adding a second degree polynomial, what does that add to a function?
Concavity.
It adds a curve, right? Yeah, concavity. So we can now match that better. But second degree only matches with the parabola. What would a third degree add to that? Third degree is going to add a little bit more curve to it, and we can go in both directions now with our end behavior, right? No.
Well, it's confusing because Cause like.
I'm gonna have to, if you want like the mathematical exact answer, I'm gonna have to think about it and get back to you.
Well, we always
It's
learn
just
like,
that-
the first derivative is like in terms of velocity or slope. The second one is acceleration or concavity.
Right.
So like adding third just adds.
But we can-
Fourth and fifth just adds more tens.
I guess in a sense, yeah.
That's weird.
Not a bad way to think about it. All right, let's do a couple of examples. Will we good? Hopefully. What?
No, I don't want to ask that question. We just kind of-
Bring it on.
Well, when we looked at the e to the x equation, the tangent line went all over the place and then slowly aligned itself.
Yeah.
And that eventually, for every equation, there will be a point where the derivative just becomes the equation again?
Then
Because-
No. Because all these functions have are infinite, right? They're all real numbers. So you'll always get somewhere, even if it's way out here, where they don't match.
But on the boundary you would?
Yeah, but what we're worried about is the accuracy within these certain intervals, so we can estimate these functions using polynomials. Right, because in the old days, they didn't have calculators.
So you can use,
Right? Seriously,
Yeah.
can you calculate sine at some value easier with the sine function, or calculate it easier with a polynomial? Because if you don't know the exact values of any sine function, it's kind of impossible.
Yeah.
Right? But you can add, subtract, multiply, divide
Yes.
your hard way. So that's part of the justification of this.
Okay.
Okay, these are good questions, by the way, even if I can't answer them all the way.
but to even do your Taylor polynomial, you need to know the sine function, because you have to know like sine at that interval.
And then the
Like pi
rest.
over 4. Yeah.
Yeah.
Okay.
Oh, joy.
But what you have on those are the unit circle values. We can use the unit circle values, which we know the values of, and estimate values around those that we don't know exact answers to.
Okay.
Instead of just.
Like sine power 4 is root 2 over 2.
Yeah, that makes more sense.
Okay, so we could say, what's the next 0.005 units away from point power 4? All right. So let's look at e to the x algebraically. We looked at it graphically, right? Let's calculate the fourth degree Taylor polynomial. Centered at 0. All right, so one thing you might want to know, and this comes up once in a while, these Taylor polynomials centered at 0, they have a different name. We call them Maclaurin polynomials.
I was wondering about that. I was on the website.
Yeah.
I thought it was his last name or something.
So Maclaurin polynomials were first, in essence. They came up with those first because 0 is really easy to do a lot of math with. And Mr. Taylor expanded that to be able to move these functions to different centers. Okay. So we call these Mac Daddy polynomials. All right, it's good stuff. So again, stay organized, and I always encourage you to write the formula out so you're memorizing this stuff, right? Okay, so what's the first term of a Taylor polynomial?
F of A
Okay, plus,
plus prime of A
yeah,
times x minus A. Well, technically, we're going back forward.
first, if you want to write that, you don't have to, but again, let's keep the pattern. Okay, next. Well, I think that's what I heard.
X minus A Squared over 2 factorial. Is it?
Okay, do you want to keep going?
No.
Okay. What degree do we need to go to?
4.
The fourth. Right. Yeah, so yeah, they can get tedious, but you know how to do it. So, all right. What is A?
E to 0.
Yeah, 0, right? So we have f at A is e to the 0.
Would the second one just be 0?
Which is 1, right?
Yes.
Okay. F prime at A, okay, we have e to the x, right? So, again, so f prime of x is e to the x, f prime of 0 is 1 again.
We go see the pattern. E to the x is one of the easier Taylor polynomials.
Okay. How about our f double prime A term?
Also 1.
Yeah, f double prime of x is e to the x. At 0, we get 1. Okay, is that going to continue?
Yeah.
It is. Okay, thank you. So these are all your coefficients for your polynomial. Coefficients. Now you're just going to plug and chug. Right, so,
So do you just get increased in smaller fractions? Should be
yeah.
1 over it's 1 to half, etc., etc., etc.
Right. So, f at 0 is 1, right?
Yep.
F prime at 0 is
1.
1,
Times
x minus
A to the x.
a, which is
1,
a 0,
0.
right? And then if you really have the desire. Okay?
So what does that prime mean for the x? Because like if you were to
Oh, the
x
x stays. I
prime,
don't think about that.
I don't follow.
Where are you looking?
So in that first factorial one, where it says 1 times x minus 0 prime, what is that prime?
So that's the first power.
Oh, so
That's a polynomial degree 1.
Okay, so in our thing we did. Oh no, no, I wrote wrong.
Yeah, that's the first power, second power.
So
Yeah,
the one
again, keep in mind,
you match it with the power.
match, match, match.
Okay.
Okay. Next,
1 times x minus 0 squared over 2 factorial.
okay. And
1 times x minus 0 cubed over 3 factorial.
Mackenzie and Isaac.
1 times x minus 0 to the 4th power over 4 factorial.
Okay. Bam. Here's your Taylor polynomial. Can you write it more simply?
1 plus x over 1 factorial plus x squared over 2 factorial plus so on.
Okay. So there's your Mac Daddy polynomial for e to the x to the 4th degree.
Are they gonna make us use these decimally?
Yeah,
'Cause that's
you could estimate e to the x at x equals 1.
and we just plug it
One
in.
shot. And again, it's going to be, you know, if it's a problem like this, and you're asked for a decimal answer, you try to calculate it, right? If not, remember your free response format, just plug 1 in and be done. 1 and done, right? You see that pattern there? Think you can memorize that? Yeah? Okay, I would encourage you to.
memorize words.
Because they will, like, one of the AP exam questions will say, write out the Maclaurin polynomial for e to the x centered at 0. And you can do all the math, obviously, you don't have to memorize this, but if you have it memorized, boom. Okay, so. But we'll get to the point where we should have these memorized because these play really big in series and sequences. Okay. So we'll make memory cards.
How far away are we from
A couple weeks,
Okay.
depending on how fast we need to go. It's up to you guys, really. Any questions on writing a Taylor polynomial?
The only question I have is like, would that be our final product answer?
This would be your answer because it's write a Taylor polynomial of degree 4, centered at 0. Got it. Okay, I'll show you some more on Tuesday, and we'll take it away from being centered at 0. So we have x, let's say x minus 2, x prime at 2, all that. It's the same process, we just have a little bit more junk in here. Okay? Awesome. Okay, let's see. We are at 8.4 for practice problems. Tuesday we'll line up with these if you want to write it down. Again, it's on Google Classroom. And then there's some spiraling.
Is it 6 or B?
It's a B and then that's A.
Oh, part B.
Yeah, so today was part A. I was going to show you example 2 and we didn't get there, so let me make sure that you're good.
So that's saying 14B, correct? B is just after B,
Yeah.
Is that 15 to 23 odd or just 15 to 23?
That's all,
Okay.
according to my hopper. So, again, 8.4a, you should be able to write these out. Part B. You can still work those. We get into a little bit more general notation on Tuesday, so if you want to wait on part B, feel free. Have a nice weekend.
You too.
Well,
You bet.
try to sleep.
I know, right?